Section 16.8, decibels. So the decibel, which is abbreviated as little d, big B, that's the unit abbreviation, dB, is a measurement unit used when comparing two different sound intensities. So because of the way of the human hearing mechanism responds to intensity, it's appropriate to use a logarithmic scale called the intensity level. So the intensity level is this variable beta here. It's a B with an extra little tail on it, another Greek letter. And it's measured in units of decibels. So if you ever hear something being a certain number of decibels, that's the intensity level that's being described there. And the way that the intensity level is calculated is with 10 decibels times the log of the intensity level relative to the threshold of hearing, I0. The threshold of hearing, I0, as we saw in the previous video, is 1 times 10 to the negative 12 watts per square meter. An important note here is if you take the logarithm of 1, then that's going to be equal to 0. So if your intensity level is the same as the threshold of hearing, then the intensity level that you get out is 0. So it sounds about as quiet as possible, right? And so this is what's measured if you've ever seen a decibel meter. It looks something like this, where there's a scale with a number of decibels, right? You can get apps for your phone that measure the decibels that they're picking up based upon the sounds coming out, right? Or if it's really quiet, it is a lower number of decibels. That number there is just giving you the intensity level. There are all kinds of free apps for your phone for it too. So you have ways to measure this, but this is the way that people talk about sound intensity levels, is with decibels. So some of them calculated, because that helps as a reference here, is using our intensity level equation with our threshold of hearing. Here's the intensity of a few different sounds, right? Our rustling of leaves is just louder than the threshold of hearing, right? 1 times 10 to the minus 11. And when we plug it into the intensity level equation, that comes out to 10 decibels. A whisper, something that's very, very quiet, it comes out to 20 decibels. Normal conversation, if you're 1 meter away, which is a reasonable distance, is 3.2 times 10 to the minus 6. That's 65 decibels, right? And it keeps going up inside a car in city traffic. Car without a muffler gets kind of loud, right? That's up to 100 decibels. That's pretty loud. Here's where it really gets interesting. When your intensity is 1 watt per meter squared or greater, like a live rock concert, that's at an intensity level of 120 decibels. And that's where, if you have sustained exposure to that intense sound level, you're going to start to have hearing damage, right? Threshold of pain is 10 watts per square meter, which comes out to 10 decibels. So notice, as the intensity increases by a factor of 10, the number of like 10 times bigger, 10 times more intense, the number of decibels only increases by adding 10, right? 120 to 130. So that's part of being a logarithmic scale. Let's try out an example of this. So we have example 9, comparing sound intensities. Audio system 1 produces a sound intensity level of 90 decibels, and system 2 produces an intensity level of 93 decibels. Determine the ratio of the intensities. Right, so we have these intensity levels, right? We have sound intensity level 1, beta 1 for 90, and 93 is what we could call beta 2 for audio system 2, its sound intensity level. The ratio of intensities then is going to be how I2 compares to I1. A ratio, remember, is always division. So that's what we're ultimately trying to solve for. And notice in our equation for the sound intensity level, right, the intensity is kind of buried. So I'd like to walk through some of the math mechanics of how we can extract that intensity from the equation, how we can turn this equation around. So the first thing we're going to want to do is we want to get the I by itself. So first I want to get the logarithm by itself. So I'm going to divide both sides by the 10 decibels. So we can do that to the left and to the right. So on the left it cancels out. And so then we have this beta divided by 10 decibels is equal to the logarithm of the intensity relative to the threshold of hearing. So now we're at an important point where we're like, okay, if we have this logarithm, how do we undo a logarithm? And this is similar to our natural log that we've seen like with adiabatic expressions, but it's not quite the same because our natural log was relative to e, but the classic log is formatted in the base 10. So the way we undo the log is we raise both sides as the exponent of the 10th power. So this beta divided by 10 decibels, I'm going to put as the exponent to the 10th power, and similarly all of this log to the I over I0 is going to be raised to the 10th power, and that undoes the log effectively. So that all that we're left with at the end is this I over I0 here. So I divided by I0 is equal to 10 raised to the beta divided by 10 decibels. And if we then want to solve for intensity, all we have to do is multiply both sides by I0. And this is now a general equation that our intensity is equal to the threshold of hearing, I0, times 10 raised to the beta divided by 10 decibels. Sorry to write over the subscript there, but I think you can still see it. So that's an equation that you can put on your crib sheet for if you need to calculate the intensity given the number of decibels, the sound intensity level, which is pretty handy. In this case, we could take the ratio of I2 over I1 and we'd see that the I0s cancel out, right? So we would be left with I2 divided by I1 is equal to, I'll show how that cancels, I0, 10 to the beta 2 divided by 10, all divided by I0, 10 raised to the beta 1 over 10. And so the I0s there would cancel, and we're left with a relatively simple expression. Since the power bases are the same, they're both to the 10 raised to some other power, we can rewrite this division as subtraction of the exponents. So I could write, I'm going to come up here, that the ratio is equal to 10 raised to the beta 2 over 10 minus beta 1 over 10. All right, so that's where we could now plug in our specific numbers of 93 and 90, and we'd be left with 3/10. So it's 10 to the 0.3 power, which we've come this far, so we might as well plug that in. So for me, I plug in 0.3, and then above my log button, I have a second option of 10 to the x power. So I'll hit that 10 to the x, and it comes out to 1.995, which in other words is going to be 2.00, which we only have 3 sig figs for this problem, so that is perfect. So that's one way to think about it. I do want to highlight one other way to think about it, because there's more than one way to approach a problem. The other way you can think about it is you could first say, okay, if I want to get this ratio of intensities, that's going to be related to what we saw at the very end there, beta 2 minus beta 1. So if I have beta 1 and beta 2 written in terms of I1 and I2, and I'm going to do beta 2 minus beta 1, which is written out here, beta 2 minus beta 1, and then we can use our logarithm rule, which says that if we have the log of A minus the log of B, then that is equal to the log of A divided by B. And this is really what we've already done, but if it's an easier way for you to think about, then that's great. If you're already happy with what we did, you don't need to worry about this too. So log of A divided by B. And that's what was done here, right? The 10 decibels stayed out in front. It sort of got factored out of this. And then we subtracted log I2 over I0 minus log of I1 over I0. So this is our A, I2 over I0, divided by B, I1 divided by I0. And when we divide these, it turns out that the I0s cancel, which is what we also had already seen, and we're left with just 10 decibels times log I2 over I1. The difference in beta is 93 minus 90, so that comes out to 3 decibels. So we can divide by 10, and we get 0.3 is equal to log the ratio of intensities. And this is where, once again, we could raise both sides to the 10 power to cancel out the log. So we get I2 over I1 is 10 to the 0.3, which comes out to 2.0. So there's some ways, another way to think about logarithms. I know they're a bit of a beast. If you have questions on them, please do feel free to ask. I'd be happy to talk more about logs. It is worth making sure you're comfortable with using them on your calculator. So that's something to check out. All right, one more section coming, and you'll be able to hear that it's on its way, as well as when it's leaving.